Hello everyone, again, this is Sidi Naajee, and we're going to continue with the theme of slopes and areas when it comes to motion graphs. So this was the last thing that we arrived at. So back in the late 1600s, Newton wondered about, okay, so if I pay attention to slopes, I would be getting some ideas about velocity and acceleration. Then he wondered, what would happen if I focus on areas instead? You know, areas of what? Areas of, any area underneath a specific curve or a specific line. What may it represent? Well, let's do it first for the constant velocity particle model, and then we'll see what we can get with the other things. So if we take a look at this here, we would see that the area under this red line here between it and the t-axis is 0. So there's nothing really that we can ascertain from that. So that doesn't help much. So let's go back, here. And then what we're going to do is, instead of concerning ourselves with slopes, instead what we will do is we will instead try to see what would happen if we focus on the areas. So in this case here, what I'd like to do, if you don't mind, here's what I'd like to do. I am going to take, let's say this is times 0. Let's say, oh, sorry, Sidi Naajee. So here we go. Let's say I want to take a certain time t later, okay? Whatever that is. Now, technically, I should have like some ti and tf. But since I'm starting at 0, so any subsequent t, that would be my tf effectively. Okay, and then I am going to say to myself here, just wonder, what in the world could, the area, in here, what could it represent? I mean, I'm just curious about that. That's what Newton did, and we're going to be as curious as Newton. So, here we go. So, area equals what? Now, I am not going to do actual numbers here. We're just looking for some ideas as to what the area could conceivably represent. Well, you know from your geometry that to determine an area, you need some kind of a length and some kind of a width, and you multiply the two together. So in our case here, we would have to multiply this dimension here by this dimension there. Okay, well, this dimension here, I'm going from 0 to t, okay? So it could express it as delta t or just plain t, okay? So the area then that we are talking about, capital A to represent it, is going to be equal to this t here multiplied by whatever this means. What in the world is this representing? Well, this is, to some degree, the velocity here. Since the velocity is not changing, this here could represent the initial velocity, the final velocity, the average velocity, or any velocity as a matter of fact. Therefore, the area here is going to be representing some kind of a v times some kind of a t. Cool or no cool so far?
Cool.
Okay, thank you. So, in this case, we've got area equals some velocity times some time. Well, I hope you guys are realizing that this is not very different from the wonderful big kahuna that we got when, we played with this. So here we go. Go check your notes. You should be able to see that we got xf equals v sub x multiplied by t plus some xi. I hope you're seeing something quite similar here. So, how could I make these two match? Well, I would have to isolate this, so I need to move the xi to the other side. So I would end up with a relationship that looks more like this. xf, subtract xi from both sides, I get xi here. And of course, the xi will disappear from the right side, and I would end up with vx times t. Now, the fact that I don't have a subscript x here, that's not a big deal. But if we see that it is related to a motion that occurred along the x, then it's no big deal to realize that this is along the x right there. And at this point though, notice how this is going to match with that, while this is going to match with that. So the area then is representing xf minus xi. Well, what in the world is xf minus xi? If you've been taking good notes and you've been paying attention, you would have realized that this is actually the change, in position, which we called the displacement. Therefore, we end up with something like this. So the area under the curve here is basically the delta x. Cool or no cool?
Cool.
Very good. Okay. Stop, please.